Assalamu alaikum. Welcome to today's subject forum on physics. My name is Ibrahim Muza, and along with me we have Mr. Ajay Kumar and Mr. Sunil Kumar. And Mr. Ajay is from Aminia School and Mr. Sunil Kumar is from Iskandar School. So we have plenty of questions. We have received plenty of questions, so many of the students. So I'll be asking questions accordingly, and some of the students would like to know the types of radiation. So, yes, sir.
There are three types of nuclear radiations. One is alpha radiation, second one is beta, and third one is gamma radiation. Alpha radiations, otherwise alpha particles emission, beta particle emission, and gamma rays. So the nature of these three things, if it is alpha radiation, alpha particles are similar to nucleus of helium atom, having 2 protons and 2 neutrons. Beta particles are fast moving electrons emitted from the nucleus. Gamma rays are electromagnetic waves of short wavelength. That's the thing.
Yeah. And Sunil sir, could you tell the properties of how these radiation can be used? How alpha, beta, and gamma can be used?
Alpha radiation we can use in smoke detector, and beta radiation we can use to checking the thickness or thickness monitoring, and gamma radiations you can use in radiotherapy. That means cobalt 60 is using radiotherapy.
Okay. And some students would like to know, do we have to know the application of radioactivity?
Definitely we have to know the application of radioactivity, because recent questions they are asking the applications. Like I have seen one question, a smoke detector they have asked.
Okay.
So it's important to know the applications.
So, and there's one question a student is asking, when it comes to detection of alpha, beta, and gamma, so we always instruct students, or in the questions, or when we describe questions, we always ask students to mention that to keep the radioactive source few centimeters close to the GM tube. So why can't we place it few millimeters instead? Will it be fine to keep the radioactive source few millimeters to the GM tube?
That also possible. We can keep a few millimeters also. Actually, if we know alpha rays are alpha particle travel very few centimeter only, so we have to keep very close to the GM tube.
Okay. So plenty of students would like to know how what half-life is and how half-life is calculated. Could you explain to us how half-life is, what half-life is and how it is calculated?
Yeah, I can explain. Actually, half-life is the time taken for the activity of the given sample to decrease by half. Activity, what is activity? Activity is the average number of disintegrations made in 1 second is activity. The activity of the given sample decreases by half in a half-life. That is one form of defining half-life. Another one is, it is the time taken for half the number of nuclei present in any sample to decay. Say for example, I can explain it a little more briefly, elaborately here. Say for example, here half-life. Half-life. It is the time taken for the activity of the given sample to decrease by half. Say for example, the initial activity is 200 counts per minute. This 200 counts per minute decreases to 100 counts per minute in one half-life. If it is, say for example, if it is 5 minutes, 5 minutes is the half-life. That 100 counts per minute again decreases to 50 counts per minute in another half-life, counts per minute. Another half-life, this is also one half-life. Here also 5 minutes. So here what's happening? The activity 200 counts per minute decreases by half in every half-life. 200 counts per minute decreases to 100 counts per minute in one half-life. 100 counts per minute decreases to 50 counts per minute in one half-life. So the time taken for the count rate from 200 counts per minute to 50 counts per minute is how many minutes? It takes 10 minutes. 10 minutes for the activity decreases from 200 to 50. So if a question comes like this, say for example, the activity of the given sample decreases from 200 counts to 50 counts per minute. What is its half-life? They can ask a question like this. The activity of the sample decreases from 200 counts per minute to 50 counts per minute in 10 minutes. What is its half-life? The half-life is here 200. We have to go like this. 200 becomes 100 in one half-life. 100 becomes 50 in one half-life. So two half-life. Two half-life, 10 minutes. Therefore, one half-life, 10 over 2, 5 minutes. Like that also you can get it. That is a simple explanation for calculating half-life.
Thank you, sir. And some students would like to know how to determine half-life using a graph. Sunil sir, could you explain to us how using a graph, a decay curve, how we can determine the half-life of a radioactive sample?
You can see in the question paper this half-life graph, decay graph. The graph will be most of the time like this way. And here, for example, here it is marked 4000. And here it is 2000. Here it is 1000.
2000.
2000, and here it is 1000. Okay. Then 2 minutes, 4 minutes, like that. This is time per minute or seconds or days, like that. This is decay rate. Then, now look, from this graph, first beginning the counts is 4000. Then we know half-life means the time taken to decay half. So 4000 to 2000, that is half, 2000. How much time taken? Check. 4000 to 2000 to reach 2 minutes taken. So the half-life of this radioactive sample is 2 minutes. Again we can check from 2000 to 1000. Okay. So 2 to 4, between 4 minus 2, again 2 minutes taken. So easily we can get from the graph. We have to check first beginning, how much is the count, then check half of that one, how much time taken. Okay.
They also would like to know how marks are allocated for such type of questions. Sometimes they are given for 2 marks and sometimes for 3 marks
3
also.
marks, yeah.
Yes. So how is marks allocated for such questions most of the times?
Some questions, there are 2 types of graphs. One is the corrected count rate against time. That will end up, the graph will finish, it will go like this way. If it is a corrected count rate against time means the graph will go and finish here. It will end up here. There is another type of graph that will be the total count rate and time. This will go like this and goes horizontally like this way. This is the background count rate. So certain questions, they will be allotting marks whether the student is aware of this background count rate. So we need to take this background, say for example, if it is 20, we need to take the 20 counts per minute and then we need to subtract it from the total count rate in order to get the corrected count rate. After that, we need to proceed the same for the corrected activity. The corrected count rate decreases by half in one half-life. Again, it decreases by half in another half-life. Like that, we have to go. So in this type of graph, they will be allotting more marks. So there are few questions in the past papers. So I can request the students to go through those type of questions and do it so that it will be very useful for them. Every year, 1 or 2 questions from nuclear physics. In this 2019, I have seen around 10 questions are there in May, June, October, November, as well as February, March. In the 3 variant papers, together around 10 questions are there. Right? Okay.
Thank you. Then what is background radiation, sir? And what are the factors, what could be contributing to background radiation?
Background radiation means always some amount of radiation in our surroundings
Okay.
because of some radioactive sources. Okay, that radiations are called background radiations. And causes of background radiation mainly rocks, radon gas, then cosmic rays, then also this nuclear waste.
So
We
sometimes
can,
yeah,
we
so-
can say this background radiation this way also. It is the low intensity ionizing radiation present in the Earth's atmosphere due to the presence of cosmic rays from outer space, radioactive materials in the rocks, etc. That is called background radiations.
So sometimes due to the nuclear wastes created by
Nuclear
the
radioactive waste,
yes.
waste material from the nuclear power station, nuclear bombs, testing, those things also will be giving background radiation.
So a student would like to know what is the relationship between an alpha particle and a helium atom? How is it related?
Alpha particles are nucleus of helium atom having 2 protons and 2 neutrons.
So there's one more thing they would like to know about the alpha particle scattering experiment. So they would like to know the whole procedure, the observations made, and based on the observations, what were the conclusions that were made? Could you clarify it for them, sir?
Using alpha scattering experiment, Rutherford concluded 3 points. First one is most of the space in an atom is empty. Second point, the nucleus having positive charge. And third point, nucleus is dense or heavy. Nucleus is very, very small and also it is heavy and dense.
A student would like to know, very general question, what is electromagnetism?
What is electromagnetism? Yeah, magnetism formed due to the current in a conductor.
Okay.
Simply.
The student, some students would like to know the rules, the right-hand grip rule, the Fleming's, in which circumstances are we going to apply the right-hand rule? So could you explain it?
Yeah, that right-hand grip rule has 3 applications. It will be better if I use the
Yeah,
board.
sure.
I can go through. Right-hand grip rule, the first application is used to find the poles. The poles. Say for example, the situation like this is a solenoid. When current passes through, this is positive negative, when current passes through this solenoid, the solenoid becomes magnetized and the 2 poles are formed. The right-hand grip rule is used to find the poles. Imagine gripping the solenoid by using your right hand in such a way, the curled fingers pointing the conventional current direction, then the thumb gives north pole. In this situation, here is north, here is south. This is one of the application of right-hand grip rule which is used to find the poles. The second one is to find the direction of the magnetic field lines. Second application of right-hand grip rule is to find the direction of magnetic field lines. Magnetic field lines. Say for example, if current passes through a conductor, there are symbols like this. Say this is a cardboard, here is a hole, you are inserting a conductor. And there is a battery here. And a switch is placed here. A switch is here. Now the switch is closed. When the switch is closed, current passes through this conductor, and around the conductor a magnetic field is produced. These magnetic field lines are forming concentric circles. By using the right-hand grip rule, we can use it in a way that we can find the direction of the magnetic field lines. How? Imagine gripping the conductor by using your right hand. Say for example, this is the conductor. I am gripping like this so that the thumb pointing the conventional current direction, and the fingers gives the direction of the magnetic field lines. So this, in this case, the field lines are clockwise. Clockwise. So this is the second application of right hand grip rule. The third application of right hand grip rule is to find the induced current. Induced current. Here, say for example, this is a solenoid which is connected to a center zero galvanometer. The point is here. If you, this is a magnet, north south, you are pushing the magnet, that is electromagnetic induction. When you push the magnet inside, the magnetic field lines are cut by the coil and an EMF is induced in the coil and the induced current flows through the coil. Now, when you push the magnet into the coil, according to the Lenz's law, there is a law, Lenz's law, the pole formed here is similar to the approaching pole north and this is south. The pole formed here is similar to the approaching pole, so we can find the poles by using the Lenz's law. Then we can find the induced current by applying the right hand grip rule. Here what is it? Imagine gripping the solenoid by using your right hand in such a way, thumb pointing north pole. Thumb is pointing north pole. Then the fingers gives the direction of induced current. The current will be like this and goes this way. The deflection will be to the right side of zero. So here there are three applications. One is to find the poles, and second one is to find the direction of the induced current, and third one is to find the direction of the magnetic field lines around the stripe conductor. Okay, sir.
So, we also used in electromagnetism topic, we also make use of Fleming's left hand rule and Fleming's right hand rule. So some of the students, they are finding it very difficult to how to apply the Fleming's left hand rule and the right hand rule. So what is the major difference between, and in what instances are we going to apply the Fleming's left hand rule and the right hand rule? Yes.
Yeah. Fleming's left hand rule is used when current causes motion. That is especially in the case of a motor, DC motor. So when, say for example, when a current carrying conductor is placed in a magnetic field, it experiences a force, the magnetic force. That we can find out by using Fleming's left hand rule. Right hand rule. Fleming's right hand rule is used to find the current direction, that is due to electromagnetic induction. Electromagnetic induction, that is when a conductor is moved across the magnetic field and it cuts the magnetic field lines and an EMF is induced in the conductor. That EMF, the direction of the current, can be found out by Fleming's right hand rule. The rule is, if the first finger, the thumb, keep the thumb and the first two fingers of the right hand perpendicular to each other. If the first finger pointing the direction of the magnetic field, thumb pointing the direction of the force, then the second finger gives the direction of the induced current.
Okay.
That's.
And what is electromagnetic induction, sir? Induction.
Electromagnetic induction. There's a
induction in
when a conductor, say, when a conductor cuts through the magnetic, if you move the conductor across the magnetic field lines, what will happen? The magnetic field lines are cut by the conductor. Whenever the magnetic field lines are cut by the conductor, an EMF is induced. If the conductor forms a part of the circuit, then the induced current flows through the circuit. That effect is called electromagnetic induction.
So could you briefly explain how a DC motor is working? How a DC motor is working?
DC motor, first we have to look the picture. Okay. Then only we can understand properly how it is working.
General, yes, sure.
DC motor, first magnetic poles is there, then coil is there, and These are the main parts of the DC motor. Okay, magnetic poles will be there, and this is coil. Then this is split ring commutator. And this is carbon brush. We know using Fleming left-hand rule, we already discussed these things. Then when the current passes through the coil, here battery, so the current is going through this coil like this direction. When the current passes through the coil, because of this magnetic field and current, a force is produced on the coil. A force is produced. That force direction we are finding using left-hand rule, Fleming's left-hand rule. So here the current is passing through like this way. So the current direction is this one, and magnetic field is this one, force is downward. So this one will be, this side will be downward, and this side will go up, moves up. And we know the coil, one side will go down, another side will go up. Okay. Then, now when the coil rotates, or when the coil moves, with that this split ring commutator also rotates. When the coil rotates, that split ring commutator also rotates. Then when the coil reach vertical position, now the coil is horizontal position, then it is going like this way. When it reaches vertical position, the split ring commutator also reaching like this way. That time commutator not touching the carbon brush. So what happens to the current in the coil? Current in the coil stops. Current in the coil stops. Now the coil is at vertical position. Because of inertia, previously it is coming like this way, because of inertia it overshoot. And the split ring commutator reverses the current direction. So when it reaches again horizontal position, this commutator, this one will reach here, this commutator will reach here. This I am giving 1, this I am giving 2. Now after that overshoot, and it, this reaches again horizontal position. Now this one will be here, this one will be here. So again this commutator touching the carbon brush. So again the current in the coil. And like this way, again because of force in the coil, the coil one side will move up and another side will go down. Okay. So that continues its rotation.
Same direction.
Okay, continues its rotation in the same direction. Okay.
Now, you have clearly mentioned about the DC motors. They would like to know a brief explanation on the AC generator as well. Sir, would you like?
Yeah. Actually, AC generator will come. That. AC generator, it is a device which converts mechanical energy to electrical energy, mechanical energy to electrical energy. A device which converts electrical energy, mechanical to electrical is called a generator. What is the principle of this one? The main principle is electromagnetic induction. Electromagnetic induction. What is electromagnetic induction? When a conductor is moved across a magnetic field, it cuts the magnetic field lines and an EMF is induced in the conductor and the induced current flows through it. In this case, it is similar. This generator, AC generator is similar to the DC motor, only 2 changes. Look at the diagram. Here there is a coil, rectangular coil, which is placed in between the poles of a powerful permanent magnet. The 2 ends of the coil is connected to 2 slip rings. That is the one change. In the case of motor, it is split ring. In the case of generator, it is slip rings. Slip rings. And the 2 ends of the coil is connected to 2 slip rings. There are 2 carbon brushes which are pressed lightly on the slip rings by using 2 springs. The coil is connected to a lamp like this. A lamp is there. This coil can move along an axle. This is the axle. Initially, the coil is rotating clockwise. It's rotating clockwise. When the coil rotates clockwise, this side I am labeling A, B, C, D. When I label this end, when it rotates clockwise by any means, by wind or water, any way, if it rotates in a way, the side AB experiences an upward force and side CD experiences a downward force. And due to this movement, the magnetic field lines are cut by the coil and an EMF is induced in the coil. And the induced current flows in the coil. This can be found out by using Fleming's right-hand rule. Keep the thumb, keep the first finger in the magnetic field, that is north to south. The force is acting upwards. Upwards is in this case out of the board. So the current is from A to B. The induced current is from A to B, and this side it is from C to D. That current comes through this way, and through this carbon brushes has come to this side, to the left side of the board. When it turns again 180 degree, what will happen? The current direction will change. When the current, say for example, one more small diagram I am drawing. Now in this case, look at the diagram clearly. The turning is like this. Here the carbon brushes are here. Everything is like this. Now you will know the difference. Now when it turns 180 degree turning, the side AB will be moving to the other side, AB. And CD comes this side. Now the current is, again this is upward force, it is rotating same direction. Now the current is from D to C and from B to A. Now this current flows through this way, through these slip rings, and the external circuit, it comes this way. So the current flows in 2 directions, that is AC. You are getting AC here. If you use the graph, of this AC waveform, this is one wave. When the coil is vertical, that is, if you start from vertical position, when the coil is vertical, no magnetic field lines are cut by the sides of the coil, and the current is 0 here. When the coil turns 90 degree, that is when it is horizontal, that is 90 degree turning, it cuts maximum field lines and the induced current is maximum. And when it is again vertical, the induced current becomes 0, 180 degree, it becomes 0. In this state, the side AB is moving upwards and upwards. After 180 degree, the side is moving in the opposite direction. So what will happen? The induced current changes the direction, and when it is horizontal again, it becomes maximum, that is 270 degree. Again, when it turns to the vertical position, that is 360 degree, the induced current is 0. And this is one cycle, time period is here. This is one cycle, one cycle. Like that, if it continuously rotates in clockwise direction, what will happen? Continuously you are getting an AC signal.
Okay.
That's it.
So basically what we saw was that in AC generators we apply the Fleming's right-hand
Right-hand
rule,
rule.
and in the DC motor we are making use of the Fleming's
left-hand rule.
Right now we'll take a short break, and we will see you in a while.
Okay.
Yes, welcome back. So a student would like to know how to determine alpha, beta, gamma, that experiment using GM tube. Could you explain the whole experiment, please?
I can explain the whole experiment. For that, we need Geiger-Müller tube, GM tube, and the rate meter and the radioactive source. I think it is better if I draw it on the board and explain. This is experiment to identify alpha, beta, or gamma radiations. Here, first of all, we need to connect the GM tube. GM tube should be connected with the rate meter. This is the GM tube, and this is the rate meter. So first connect the GM tube with the rate meter. Without keeping any radioactive source in front of the GM tube, note the background count rate. That may be around 20 counts or 25 counts, 20 counts per minute. Note it down. Then keep the radioactive source just 3 centimeter away from the GM tube, quite close to it, 3 centimeter away. Why we are keeping 3 centimeter away? Because sometimes the source emits, if it is emitting alpha particles are having short range, so it will not reach a detector. So we will say that alpha particles are not present, but it may be present inside because it has very short range, nearly 5 centimeters. So you are keeping 3 centimeter away from the GM tube, the radioactive source you are keeping. So after keeping the radioactive source, note the count rate, the total count rate. Say for example, it is around 2000 counts per minute. When you keep that radioactive source, the count rate is 2000 counts per minute. Then introduce a paper, a thin sheet of paper, between the radioactive source and the GM tube. If you keep a thin sheet of paper, the count rate remains 2000 counts per minute. There is no decrease in count rate. If there is no decrease in count rate, then there is no alpha particle. There is no alpha particle. Sometimes when you keep the paper, the count rate falls to 20 counts per minute. Then we can say that it is having only alpha particle. Okay. Only alpha is present inside. Some other situations, it may be around 1500 counts per minute. Then we can say that the count rate decreases, that is because of alpha, and also it is not to background, so some other radiations like gamma or beta is present. We are not sure about that. For that, what we need to do next, we need to replace the paper or keep the paper as it is. Besides the paper, you can keep a thin sheet of aluminium. Right. If you keep a thin sheet of aluminium, if the count rate remains as it is, like aluminium, after keeping aluminium, the count rate remains as it is 2000 counts per minute, there is no alpha particle and there is no beta particle. If the count rate, no alpha and no beta in this case. If the count rate decreases to background 20 counts per minute now, then the beta particle only present. If the count rate decreases to 500 counts per minute, beta particle is present as well as the gamma radiations are present. Like that, by using paper, we can identify, we can find out whether the source emits alpha particle. Okay. By using aluminium, thin sheet of aluminium about 5 millimeter, we can check whether the source emits beta particle. And if you want to finalize it, thick sheet of lead will show clearly the gamma radiations. Yeah. Like that, we can identify.
So then, when we say when a radioactive nuclei is emitting alpha particle, it is called an alpha decay. And then likewise for gamma and beta also. They would like to know with a simple equation, could you explain the decay process for alpha, beta and gamma?
The decay equation. Oh.
For that alpha decay, beta decay and gamma decay. Alpha decay, we have to remember this one, alpha 2,4, that is same as helium nucleus or helium. Okay. Then first we have to understand when an alpha decay occurs, what are the changes in the parent nucleus. For example, I'm writing uranium-92 235 radioactive nucleus. This one emitting one alpha particle. Alpha particle means alpha. Okay, emitting from this one alpha particle is emitting. So what will be the new element's atomic number? We can check new element this from this. When an alpha decay occurs, atomic number decreases by 2. Look, 92 minus 2, 90. And mass number decreases by 4. So it is 231. That is another element thorium. Now look, when alpha decay occur means the new element atomic number less than 2 and mass number less than 4. So when we add these two, 90 plus 2, we will get this 92, 231 plus 4, 235. Okay. Then beta decay. Beta, this is beta symbol. Then when a beta decay occurs, what are the changes we can say? For example, same uranium 92, 235. A beta decay occurs. So one beta particle is going out from this nucleus. So when a beta decay occurs, atomic number increases by 1. That means 93, and mass number, there is no change, 235. So new element atomic number and mass number. When we add this to 93 minus 1, 92. Then 235 plus 235. Okay. In the case of gamma decay, there is no change of, for example, uranium 92, 235, gamma decay. There is no change of atomic number and mass number, only energy change. Okay.
Yes. So it's most of the time after an alpha decay or a beta decay, if it is having excess energy, so that in order to get rid of it, they emit it in terms
gamma
of,
rays.
yes, in the form of gamma rays. I think they're having plenty of students are having issues with half-life. I think so. We got another question to explain how to calculate half-life.
How to calculate half-life?
Yes.
Yeah, already we from the graph we discussed.
Yes. With a sample question, say for example, in terms of reduction in radioactive nuclei, I think both ways, in terms of radioactive nuclei or in terms of activity, both ways. Could you say?
Okay, I can explain some 2-3 questions,
Yeah.
simple questions, how to calculate the half-life by using both activity and half-life calculations. Question 1. You know that the activity of the given sample decreases by half is 1 half-life. So here the activity of the sample is 2000 counts per minute. The 2000 counts per minute decreases to 250 counts per minute. This is one type of question. 2000 counts per minute decreases to 250 counts per minute in 1 hour. What is its half-life? Question. How can you find this question? Say, this is the activity decreases by half. Say 2000 decreases to 1000 in 1 half-life. 1000 decreases to 500 in another half-life, again 1 half-life. 500 becomes 250 in counts per minute in 1 half-life. So total how many half-life? 2000 to 1000, 1 half-life. 1000 to 500, 1 half-life, 2. 500 to 250, again 1. So total 1 plus 1 plus 1, 3 half-life. 3 half-life, 1 hour. Therefore, 1 half-life is 1 hour is 60 minutes. 60 over 3, that is 20 minutes. So 20 minutes is the half-life. So here the half-life, the activity of the given sample 2000 decreases to 1000 in 20 minutes. 1000 becomes 500 in 20 minutes. 500 becomes 250 also in 20 minutes. This is one type of question. You can find the half-life from this. Sometimes they may give questions like this. Given the half-life is given 5 minutes. They may ask questions like, what fraction of the activity remains after 10 minutes? What fraction of the activity remains after 20 minutes, for example, 20 minutes. In this question, they have given only the half-life. They are asking what fraction after 20 minutes. So you should have to find out here 1 half-life, 5 minutes. 1 half-life, 5 minutes. Therefore, 20 minutes, how many half-lives? X, find it first. X is equal to 20 over 5, 4 half-life. First of all, you need to find out how many half-lives here, 4 half-lives. Fraction begins with the 1. So first initially the activity is 1. 1 becomes half in 1 half-life. Again it decreases by half, that is 1/4. Second, then third half-life 1/8. Finally it becomes 1/16. Total 1, 2, 3, 4. 4 half-life. So what is remaining now? 1/16 of the activity remains. How much decayed? 1 minus 1/16. That is 15/16 decayed. So like that also questions will come. This is one type of question. The second question. There are many questions there. Say sometimes they may ask questions like this. The background count rate is 20 counts per minute. The count rate, the total count rate from the sample is 2020 counts per minute. This is total count rate. The half-life is 5 minutes. What is the count rate after, what is the total count rate after 15 minutes? What is the total count rate after 15 minutes? The question is, given that the background count rate is 20 counts per minute, the total count rate initially at the start is 2020 counts per minute. Half-life is 5 minutes given, and the total count rate after 15 minutes is the question. What is the total count rate after 15 minutes? First of all, we need to find out the corrected count rate. Corrected count rate is total count rate minus background count rate. Background count rate. So what is the total count rate? 2020 minus 20, that is 2000. 2000 counts per minute is the what? The corrected count rate at the start. Then we have given the half-life 5 minutes, and after 2000 becomes 1000 after 5 minutes. That is one half-life. 1000 becomes 500 again after one half-life. 500 becomes 250 again one half-life. Like that 1, 2, 3. 3 times 5, 15. 15 minutes over. What is the total count rate? Total count rate is 250 plus we need to add the background count rate, which is 20. So 270 is the count rate. This is the total count rate recorded after 15 minutes. Like that, different types of questions are there. You can do as much as past paper questions so that you can improve in the exam.
Thank you, sir. A student would like to know the major difference between nuclear fission and nuclear fusion. So what's the difference between nuclear fission and nuclear fusion?
Nuclear fission means large nucleus break into smaller nuclei, and with that a lot of energy also releasing, and neutrons also.
Okay.
And nuclear fusion means small nuclei join together form a large nucleus, and with that also a lot of energy releasing, and neutrons also.
I think it is it there in the syllabus now in 2020 syllabus?
So it's
They have asked questions like
yeah,
that, right?
a few questions they have asked. So
Okay.
generally knowing that would be fine,
Fine,
but
yeah.
it's not specifically mentioned there. Then student is asking sometimes we are using as an application of electromagnetic radiation. Radiation is used as a tracer. So why is alpha not used as a tracer, but instead they are making use of gamma or beta? So why exactly are they using, why they are not using alpha as a tracer?
Alpha particles are having less penetrating power, so it cannot penetrate out of the body if it is used in body or checking the leakage in underground. Alpha particles are having least penetrating power. So if you are using tracer in our body, say for example checking the function of thyroid glands, the patient should be given a solution of iodine 123 to drink, which emits gamma radiations and also which has a short half-life. So short half-life in the sense it will decay quickly so that it won't affect the body, as well as it has high penetrating power, gamma rays are coming out, so that by using a detector from outside we can check the amount of radiation coming out from the gland, which will give a clear idea about the function of the thyroid glands.
So,
So that's why alpha is not used, because it has less penetrating power.
So then it can be used in industrially as well to check for leaks and these things also. Radiation can be used. So a student would like to know how they are using the radiation as a tracer to determine leaks in pipes, water pipes. So could you explain in water pipes how they will use radiation, radioactivity to determine leaks in water pipes underground as a tracer?
Water pipes, actually we are passing radiations, radiations from one side, and above that we are checking, we are keeping this detector, and if the leakage is there means that area we will get the in the detector more count rate will be.
In this type of checking, we are using in the pipelines sodium salt is used, which is emitting gamma rays, which can be easily penetrating through the metal pipe and through the soil and reach the detector. So the leakage area contains, if you move the GM tube with the detector, when the leakage part comes, there is a sudden increase in count rate.
Because
The
there's
increase,
a leak.
there is a
because
leak and so many particles are available there. So there is a large increase in the count rate. So that we need to mark it and we can dig it and find out the leak.
So instead of digging the whole
whole
area,
area,
so
yeah,
they
yeah.
can
Easily
specifically go there. Okay. And one student would like to know, why do you say it's random? Is mentioning about the radioactive process, we are always stating that the whole radiation process is random. So is it very important to mention that the process is random, and why do we say it's a random process?
Yeah, it's a good question. Random means irregular. Irregular in, we cannot predict which nucleus is going to decay in a particular time or in a particular direction. Two important things, random in direction as well as random in time. Random in direction means if you keep the radioactive, say this is the radioactive source. If you keep the GM tube this side also, you will get the count rate. Here also you will get the count rate. All the sides you will get the count rate because it is radiation comes everywhere. And also we cannot find out, we cannot say that in 5 minutes 200 counts only will come like that. Because the number of particle decay in unit time is not constant. It varies. That is the random nature in time. So random is very important.
Okay. So it's like sometimes in the questions also we find instead of random, it could be, they could sometimes use words like spontaneous even, right?
Yes.
So,
Random and spontaneous.
So it's like they not specific, they might use different words even, but meaning is basically the same. Yeah, and the student would like to know what actually happens inside a GM tube when the radiation goes in. So what happens inside the GM tube? So what property of the radiation is making these detections actually? What property is enabling the
ionizing property of the nuclear radiation.
Yes. Then what happens inside the GM tube?
Inside the GM tube, there is a gas which is called argon. At very low pressure, that is nearly 1/7 of the atmospheric pressure is present. When the nuclear radiation gets inside the GM tube, it ionizes the air, the gas particles, the argon. It produces argon gas and ions. So argon gas and ions are there, and there is a wire at the central wire which is positively charged wire. So the electrons are accelerated, the negative charges are accelerated towards that one. Because of that movement, the gas conducts. A current pulse flows in the circuit. This pulse can be recorded by the rate meter.
So it's basically higher the ionizing, greater the reading. Yes. Student would like to know. So we all know that alpha and beta both they are having a charge. So they can be easily deflected inside an electric and magnetic field. But how we are going to apply, how we are going to determine to which direction will an alpha or beta particle deflect when it is passing into an electric field. So could you explain here?
So electric field, positive charged plate and negative charged plate. Okay. Then if a radioactive source here, okay, then alpha. Alpha we know positively charged particles. So alpha will go to which side? We can check. Alpha will go to the, alpha is positively charged particle, so positive and positive will repel and it will go to the negative side. And beta, if this is alpha, if it is a beta source means, beta radiation means it will go to the positively charged plates. And the gamma rays will go in a straight line. And magnetic field.
Yes, magnetic field also. I think that would be better.
We know alpha is positively charged and north magnetic field, this is magnetic field north and south poles, and north is same as positive and south is same as negative. So alpha source is, alpha radiation is emitting means it will go to the south side. If you are keeping a photographic plate or fluorescent screen, you get the things. Then beta will go to the negative, this beta having negative charge, so it will go to the north side, and gamma will go straight. And beta will deflect more than alpha because beta is having less mass.
So in
But
an, yeah.
here we can apply the Fleming's left-hand rule
Yeah.
to find the direction of the force acting on the charged
Yes.
particles.
So you can explain in terms when the magnetic field is into the medium. Could you explain that when the magnetic field is into the medium using the Fleming's left-hand rule?
This one. Beta particle, alpha particle.
Yeah, anything would be fine.
Yeah. For example, one beta particle is going into the magnetic field is into the page. Okay, this is magnetic field is into the page. One beta particle is going like this way, beta particle. And most of the time, the questions are coming like this way, beta particle. Then we have to check beta particle, this particle will deflect this side or this side. For that, we are using Fleming's left-hand rule. And we know beta is same as electron, so electron flow and current flow we have to remember. We know electron flow and current flow is just opposite. Okay, so electron flow is this direction, so the current flow is this direction. Okay, now I am using this left-hand rule. Okay, magnetic field is into the page. Magnetic field, this is magnetic field, this current, this is force. So magnetic field is into the page, and current is this direction. Okay, from this side it is little more clear. Magnetic field is into the page, current is this direction, opposite of beta, and force is downward. So this will deflect this direction. Okay.
Yes.
Then, for example, if it is an alpha, source, then alpha we know it is same as this positive.
Conventional current, yes.
So alpha will deflect this direction, current direction. Okay, alpha is same as convection current direction. So the current will be like this way. Current is, magnetic field is into the page. Magnetic field is into the page. Current is this direction. Force is this direction. So it will go up.
So in all instances, alpha and beta will always be deflecting to
In
the
the opposite
opposite
direction.
side. Yes.
Yeah,
And moving away from radioactivity, a student would like to know why are we referring iron as soft iron? Why are we saying it's soft iron?
Because it's actually iron is a soft magnetic material. Soft magnetic material, so it is called as soft iron. It's not like soft when you touch it.
Okay.
It is soft magnetic material, that's why it's
Yes.
called as.
And how to simple ways how to magnetize a material using a solenoid. So how to magnetize an iron bar? Are we using a soft iron, or are we supposed to use a hard magnet like steel? So we are making use of steel, right?
Steel, yeah,
So
because-
the student would like to know how to make use of that process, how to permanently magnetize a steel using a solenoid.
That's we have to keep the steel inside a solenoid and pass DC through it. It becomes magnetized. So here we have to apply the right hand grip rule to find the poles.
Okay. So so that our time is up. So thank you very much for coming here.
Yeah, thank you.
Yes. So that concludes our session. So we'll hope to see you in our next physics forum. And thank you for watching. And wassalamu alaikum.
Thank you.